How are you doing? I hope everyone is safe, healthy, and hydrated. In this video, we will be discussing how to set up and evaluate double integral in the Cartesian coordinates. I'm RD, and let's begin. Recall that, given a function f defined by y equal to f of x, and an integral f of x dx evaluated from a to b, if f of x is greater than or equal to 0 for all x element of the closed interval a to b, then the integral f of x dx evaluated from a to b is an area of some region. Now for the double integrals, we are given z, which is a function in terms of x and y that is bounded on a region R on the xy plane. The double integral is denoted as this, and it can be read as double integral of f of xy dA evaluated on the region R, where dA can be expressed either dy dx or dx dy. Now, let us visualize how this double integral works. Consider the graph of the function z plotted over a region R on the xy plane. Our goal here is to find the volume of the solid formed bounded by these graphs. In order to get this, first, we want to divide the region R into subrectangles with area dA. Every subrectangle has a dimension dx by dy. And this gives us dA equal to dx dy or dy dx. Now to get the volume of our rectangular prisms formed from every subrectangle, we need to find its height. Consider a point xy on an arbitrary subrectangle on R, and consider its corresponding function value on z given by f of xy. Notice that the distance between these points is given by f of xy itself. Thus, f of xy is the height of every rectangular prism. Hence, for the volume of every rectangular prism, we can get it by simply multiplying f of xy to dA, where dA is the base or area of the base, and f of xy is the height. And the sum of the volume of these rectangular prisms could give us an approximation of the volume of the solid formed by plotting the function z equal to f of xy over the region R. Again, in double integrals, we are given a function z equal to f of xy that is bounded on the region R on the xy plane, and it is denoted by this. Now let's talk about on how to evaluate double integrals. First, we choose the order of integration. That is, we set dA to be dx dy or dy dx. On the later part of this lesson, we will find out that the order of integration would matter depending on the orientation of the strip, that is either vertical or horizontal strips, on approximating the area of the region R. Second, we express the region R as bounds for the integrals. If we set dA to be dx dy, we consider the bounds for x, x1 and x2 as bounds for the inner integral, and the bounds of y, which is y1 and y2, as bounds for the outer integral. The other way around goes if we set dA to be dy dx. These double integrals are now then considered as iterated integrals. Why? Let's see on the succeeding slides. Third, we evaluate an iterated integral, one integral at a time, starting with the innermost integral. How to do so? Let's consider an example. In this example, we are given z equal to f of xy, and it is bounded by a rectangular region R with a set of ordered pairs xy, where x is from a to b and y is from c to d. Then our double integral f of xy dA evaluated on the region R can be expressed as the following. First, we have an integral from c to d, integral from a to b, f of xy dx dy, and it is equivalent also to the integral from a to b of integral from c to d of f of xy dy dx. Consider this first integral. We first integrate f of xy with respect to the variable x and evaluate it from a to b. Upon evaluation, we then integrate the outcome with respect to the variable y and evaluate from c to d. The other way around goes on the second integral. Now remember, to evaluate the integral f of xy dx, we consider the variable y as a constant. And to evaluate the integral f of xy dy, we consider the variable x as a constant. Now let's move on to this example. We have a double integral of 2x plus y minus 2 dA evaluated on the region R, where R is the set of ordered pairs xy, x goes from 1 to 2, and y goes from 0 to 3. First thing that we must do is we illustrate the region R. Take note, R is given by this set of ordered pairs, and from here, x is bounded from 1 to 2, while y is bounded from 0 to 3. So for the solution, if we set dA to be dy dx from the previous slide, we then consider the range of values for the variable y to be the bounds of the innermost integral, that is from 0 to 3. And for the outer integral, we consider the range of values of the variable x to its bounds, that is from 1 to 2. Hence, this will be our iterated integral. Now let's try to evaluate this integral. First, we integrate the innermost integral with respect to the variable y. Note that in integrating this, we treat the variable x as a constant. Integrating 2x with respect to y will give us 2xy. Positive y will give us y squared over 2, and negative 2 will give us negative 2y. Now, evaluating the bounds from 0 to 3, we then have the following integral, which is the integral of 6x plus 9 over 2 minus 6 dx evaluated from 1 to 2. Or simply, we can write this as the integral of 6x minus 3 over 2 dx evaluated from 1 to 2. Finally, we integrate this integral with respect to the variable x. 6x will become 6x squared over 2, and 3 over 2 will become 3 over 2x. Now, evaluating this from 1 to 2, it will give us this by substitution, and later on, it will give us 15 over 2. Now consider the same example, but this time, try to set dA to dx dy. This time, we set the range of values for x, 1 to 2, as the bounds of the innermost integral, and the range of values for y, 0 to 3, as the bounds for the outer integral. Now, evaluating this integral will be left as an exercise. But rest assured that we can get exactly the same volume when we set dA to dx dy. That is 15/2. Now, we observe that if our region R is rectangular, it is very easy for us to set up the iterated integral. But what if the region R is not rectangular? For example, consider the region R bounded above by g of x, bounded below by h of x on the interval a to b. If we use vertical strips to find the area of the region R, we set dA to be dy dx. Hence, our integral, the double integral f of xy dA evaluated on the region R will become this, where the innermost integral is bounded by the upper and lower bounds of region R in terms of the variable x, and the outer integral is bounded by the leftmost and rightmost bounds for R. Here, consider a region R bounded from the right by g of y, from the left by h of y on the interval c less than or equal to y less than or equal to d. In this example, it is convenient for us to use horizontal strips to find the area of the region R, thus setting dA to be dx dy. Hence, our iterated integral double integral of f of xy dA evaluated on the region R will become this, where the innermost integral is bounded by the rightmost and leftmost bounds of region R expressed in terms of the variable y, and the outer integral is bounded by the upper and lower bounds of region R. To visualize how this works further, let's consider an example. In this example, we have a double integral of x plus y dA evaluated on the region R, where R is a region bounded by y equal to x squared, y equal to negative x, and x equal to 2. The first thing that we must do is investigate how the region R looks, so it would help us to determine the bounds of integration. Plotting the region R, we have this. Notice from the graph that R is bounded above by y equal to x squared, bounded below by y equal to negative x, and x varies from 0 to 2. Now consider setting dA to be dy dx. That means we will be using vertical strips to find the area of the region R. For the bounds of the innermost integral, we consider the upper and lower bounds of the region R and express them in terms of the variable x. So we have negative x and x squared. Now for the bounds of the outer integral, we consider the leftmost and rightmost bounds of the region R. Take note, here, x varies from 0 to 2. Okay, let's try to evaluate this. Integrating the inner integral with respect to the variable y, we have this integral. Then evaluating the bounds negative x and x squared, and upon simplification, we have the following. The integral of x raised to 4 over 2 plus x cubed plus x squared over 2 dx evaluated from 0 to 2. Now, we integrate this with respect to the variable x. We have x raised to 5 over 10 plus x raised to 4 over 4 plus x cubed over 6 evaluated from 0 to 2. And evaluating the bound 0 to 2, we get this, which gives us the answer 128 over 15. Now at this point, we try to set dA to be dx dy. That means we will be using horizontal strips to approximate the region R. But observe that on the negative y-axis, region R is bounded from the left by y equal to negative x, while on the upper y-axis, R is bounded from the left by y equal to x squared. Thus, it will require us two integrals to find the area of R using horizontal strips, giving us also two integrals to set up the iterative integral for this example. For the first integral, consider the region R in the positive y-axis. The innermost integral will be bounded by the rightmost and leftmost bound of region R, and we express them in terms of the variable y. That gives us x equal to 2 and x equal to the square root of y respectively. For the outer integral, we consider the upper and lower bounds of R. Thus, we have from 0 to 4. For the second integral, consider the region R in the negative y-axis. The innermost integral will be bounded by the rightmost and leftmost bound of region R, and we express them in terms of the variable y. That gives us x equal to 2 and x equal to negative y respectively. For the outer integral, we consider the upper and lower bounds of R. Thus, we have from negative 2 to 0. Evaluating this integral will be left as an exercise, but take note that the answer should also be equal to 128 over 15. Now for some remarks, if h equal to h of xy is the height of a solid over a region R, then the double integral h of xy dA evaluated on R is the volume of the solid. Meanwhile, the double integral dA evaluated on the region R is the area of the region R. Now here's how our previous example looked like. We have the region R here, shaded in yellow, and plotting z over this region will give us this solid. And the volume of this solid is given by the double integral x plus y dA evaluated on R, which is equal to 128 over 15 cubic units. So far, on the previous examples, f of xy is always predetermined as well as the region R. Now, what if we are only given equation of a solid? How are we going to set up the iterated integral then? For example, set up the iterated integral that solves for the volume of the tetrahedron bounded by the plane 3x plus 2y plus z minus 6 equal to 0 and the coordinate planes. The first thing to do is to see how the graph of this equation looks like. Luckily, in this example, it is easy to graph this equation by just considering the intercepts of the plane, which are the triple-ordered pairs 0, 0, 6, 0, 3, 0, and 2, 0, 0. Now, how do we get dA and h of xy? Note that h of xy is the height of the solid formed and is given by h of xy equal to 6 minus 3x minus 2y. We can get this simply by isolating z in the equation of the plane or by expressing z in terms of the variable x and y. Now, how can we get the bounds for dA? By setting z equal to 0, we get the following equation: 3x plus 2y minus 6 equal to 0. And then we investigate the region bounded by this, on the first quadrant on the xy plane. Hence, the volume given by the double integral h of xy dA evaluated on R will become the double integral of 6 minus 3x minus 2y dA evaluated on R. And suppose we set dA to be dy dx. That means we will be using vertical strips to find the area of the region R. For the bounds of the innermost integral, we have to express the upper and lower bounds of R in terms of the variable x. Note that R is bounded above by the line y equal to 6 minus 3x over 2, this line, and bounded below by y equal to 0. For the outer integral, R is bounded from the left to right by x equal to 0 and x equal to 2 respectively. Thus, the integral will become this. Evaluating this integral and setting the integral using dx dy will be left as an exercise. Another example. Set up the iterated integral that solves for the volume of the solid in the first octant bounded above by the paraboloid z equal to x squared plus y squared and the cylinder x squared plus y squared equal to 4. Observing the figure, we can deduce that a solid form has a height of h of xy equal to x squared plus y squared. Now, our concern here is how region R look like on the first quadrant on the xy plane. On the figure, we can observe that the solid is bounded below by the cylinder, giving a way for us to investigate the graph of the cylinder on the first quadrant on xy plane. Hence, the volume of the solid is given by the double integral of x squared plus y squared dA evaluated on R. And in this particular example, we set dA to be dx dy, meaning to say we will be using horizontal strips to find the area of the region R. For the bounds of the innermost integral, we have to express the leftmost and rightmost bounds of R in terms of the variable y. R is bounded from the right by x equal to square root of 4 minus y squared and bounded from the left by x equal to 0. While for the bounds of the outer integral, R is bounded above by y equals 2 and bounded below by y equals 0. Thus, the volume of the solid is given by this integral. Evaluating this integral and setting the integral using dy dx will be left as an exercise. And that ends our discussion for today. I hope everyone learns a lot from this lecture. Goodbye, and thank you for listening.
If you want to learn more about topics on Math 28, check out these videos. And don't forget to answer the exercises found in the description below. Have a good day. Bye!